Good day, ladies and gentlemen. My name is Johan van der Borgt and I am an ESD design specialist from Sofics. I will talk to you about how you can optimize the ESD protection for low power and high speed interfaces based on Silicon Controlled Rectifiers, or simply called SCRs. These solutions have been verified on both 4 and 8nm FinFET processes from Samsung Foundry. First, I'll shortly introduce what's ESD all about and why on-chip ESD protection is required. Then I'll explain the typical protection setup for FinFET technologies and what can go wrong. Next, I'll come to how these challenges are countered by Sofics in various processes from Samsung Foundry and make some conclusions. Are you ready? Let's start with ESD. So, what is now ESD? Electrical charges are everywhere, and when such a charge hops from one location to another, it is then that we call it an electrostatic discharge. Such a discharge has typically a very short duration, typically less than 1 microsecond. And such a discharge is very abrupt, which means that its voltages and currents have a very short rise time. Furthermore, those discharges can reach extremely high current levels, up and over 210 amps. It causes various destructive changes on silicon, like melting of junctions, or melting of metals, or just junction or gate oxide breakdown. This occurrence can happen anytime, from the first production steps in fabs till packaging and test. For the rest of its lifespan, a chip will be susceptible to ESD strikes. So let's now have a look at what we call a typical traditional protection for FinFET technologies. And also let's have a look at what challenges and problems you may expect with this approach. Traditionally, the protection of an analog I/O circuit against ESD is very simple and straightforward. You use a diode from ground to your I/O path and a diode from your path to your power domain, and that's it. It comes with quite a number of good characteristics, like low IDDQ leakage current, low parasitic capacitance, and it consumes only a small area to fit in. If we look what happens during an ESD strike between path and ground, you'll see that the current from the discharge will take quite a tour. It travels through your diode, over the resistive power bus, through the power clamp, and along the resistive ground bus to arrive at the ground path. It passes thus a lot of components, and each adds up to the total stress voltage, which will be seen over what is called the victim structure. This stress voltage may not exceed the critical failure voltage of your gate oxide or junction. As you can imagine, it really doesn't help that with more advanced technologies the conditions get worse. For instance, the maximum allowed current density through diodes decreases. Another issue is that the metal resistance increases. And if that's not bad enough, those tin oxide transistors, which need to be protected, get way lower failure voltages. What has Sofics now done to protect the circuitry in the 4nm and 8nm nodes from Samsung Foundry? Let's first take a look at the SCR-based solutions for the different power domains. Remember, for a typical approach, the power clamp is in your I/O's discharge path. For the protection of a 1.2 volt power domain in 4 nanometer, we built a clamp around our proprietary SCR body. We validated it through an MPW run and verified it on silicon. As you can notice, we got a 5.5 amps failure current during a 100 nanoseconds TLP test. From a DC test, we got less than 25 nanoamps of leakage at room temperature. And leakage at 125 degrees C was still lower than 2 microamps. The complete solution as is fits in less than 1200 square microns, or, if you like, less than 2 square mils. When you look at the clamp we provided for the 1.8 volt power domain, the failure current is over 6 amps for TLP tests, and even over 8 amps when running VF-TLP tests. Leakage is less than 1 nanoamp at room temperature and less than 800 nanoamps at 125 degrees C. The area for this clamp was less than 2800 square micron, and this can probably be further reduced to get closer to a 2 kV solution. Another advantage is that our design allows for easy modification. If you need a different holding voltage or a higher or lower trigger voltage, for instance, then it is easy to modify your design. As you can see from these curves, a small modification makes that the blue curve move up to the red curve. All these modifications are or will be validated on silicon for different processes. So far for some of the possible approaches to protect the power domain. Let's now have a look at how we can protect your IOs. First of all, at Sofics we believe in the local clamp approach. This means that all ESD current dissipation happens locally. Because you work locally, you don't need to rely on buses and don't have to take care of bus resistances. Since the current doesn't flow through any additional devices or metal lines, it means that the stress voltage is well defined and can be adapted and optimized to stay below the critical failure voltage of your oxide or junction. Also, if you need something specific like higher trigger levels, reduced capacitance, or over voltage tolerant devices, which is something that is almost impossible to create with diodes, it still can be created or adjusted to your needs. As an example, we take next structure, which is a full local clamp for a 1.2 volt I/O. This clamp, like it is here, can handle all possible stress cases, which means I/O to ground, I/O to VDD, VDD to I/O, and ground to I/O. We've built a structure in a 4 nanometer process targeting 2 kV HBM, and it turned out to achieve a 1.3 amps failure current in a TLP test. When performing a VF-TLP test, the current was well over 5 amps. I/O leakage was below 5 nanoamps, and the complete structure fits within an area of less than 370 square micron or less than 0.6 square mils. If we take a look at the complete I/O containing this local clamp together with the I/O circuitry, you can see that the clamp size is really limited. And you can also see on this curve that this device easily can handle the current needed to protect the I/O from strikes over 2 kV. If we keep on thinking along these lines, we can also come to a point that you need, for instance, a clamp to protect your circuitry for another protection level. In that case, in case you solve the problem locally, you don't need to beef up your power clamp and you don't need to adapt your power bus because there's no differing current flowing through it. We also validate the scaling of our solutions on silicon. Here we made a 4 kV solution and the scaling matches perfectly. It does not mean that we just put two devices next to each other. No, the device itself will be scaled. Here we did some upscaling, but this also applies for downscaling to, for instance, 1 kV of course. So also the scalability of our solutions will be validated on silicon. We also created a slightly modified version of the previous 1.2 volt clamp to fit for the 1.8 volt domain and created some variations to alter the holding voltage. In this case, we could range the holding voltage from 1.65 volts to 3.6 volts, thus allowing the best clamp depending on what the I/O circuitry looks like. If we think then about CDM, because we've been talking now a lot about HBM already, we'd rather look to the VF-TLP curves. A VF-TLP, or very fast transmission line pulse, is a 1 nanoseconds pulse with a 200 picoseconds rise time. If we apply this pulse to the local clamp we just talked about, then you can see that these clamps easily can handle currents well over 6 amps. But very often we provide these type of clamps to protect very high speed interfaces like SerDes, RF or photonic interfaces. These interfaces require a very low RC load, so no ESD resistance is allowed in the path, and only very low parasitic capacitive load. The signals are also usually very small and thus have a low bias voltage so that everything can be operated with high-speed tin oxide transistors. This makes everything very sensitive to ESD, so you need a dedicated and working solution. Sofics has solutions for interfaces where you need very low capacitive load. You'll find them usually in high-speed or high-frequency interfaces where you need a low RC and where tin oxide transistors are used. Because of these transistors, you cannot allow for large ESD overshoots. What we typically see is that the performance and the load needs a trade-off. If we compare our clamps against the standard solution, we can improve performance for the same load or lower the load cap for the same performance. Any customization is possible. Let's see how we got this up and running in Samsung Foundry's 8nm process. Here the SerDes interface runs in a 0.85 volt power domain. The circuitry has a T-coil approach and requires protection over the 4 stress cases I mentioned before. Sofics provided a local clamp consisting of 2 ESD-on SCRs with a footprint of less than 820 square micron. The clamp got integrated in the T-coil design and was thus placed in parallel with the RX and TX circuits. The resulting curves from the TLP analysis can be seen here. When applying positive stress from path to ground, the SCR becomes active, and you can notice this through the small snapback in the curve at around 1.5 volts. With stress from path to VDD, all current is conducted through the integrated diode. In both directions, the device reaches over 1.5 amps before degradation kicks in. The measurements on silicon revealed that the device could handle plus and minus 2 kV HBM and over 5 amps of CDM current. It is latch-up safe according to JEDEC 78 Class 2 Level A and has less than 1 nanoamp of leakage. The construction did not require any special layers like ESD implant or deep N-wall. So, let's review what we got and conclude this presentation. First of all, when we talk about FinFET processes, we talk about tiny, very sensitive transistors that have low failure or breakdown voltages. The way that traditional ESD solutions work involve a lot of structures which each causing a voltage drop along the discharge path. These add up to the total stress voltage, and these voltages increase due to their nature. It results in an increased design complexity combined with a high cost for a design respin in case of a failure. Sofics has solutions, often based on SCRs, but I have to say also with other structures, has solutions to protect your ICs both for power domains as IOs, even when those IOs are created with core devices. Depending on and due to the way the clamps are built, we can choose from a number of possible solutions to fit your needs. It will give you an advantage over your competitors in, for instance, area, capacitance, leakage, or whatsoever. Solutions for Samsung Foundry's processes are already available or are in production and qualification. Right now, we have low cap solutions for 8 nanometer and 4 nanometer processes, with additional types of solutions in production. 5 nanometer solutions have been defined and are recently taped out. Several other tape outs are planned, like the upcoming one for specialty I/O. Development of solutions for the 14 nanometer process are planned to start in the first quarter of next year. So, this concludes my presentation. I thank you for your attention and invite you to visit us on the booth during SAFE 2021 or to contact us by sending an email to info@sofics.com.